In this video lesson, we're going to look at spectroscopy and how we can use spectroscopy to identify what organic compound we're working with. So first of all, we need to be able to calculate the index of hydrogen deficiency, or the IHD, and it measures the degree of unsaturation in an organic compound. So remember, when a hydrocarbon is saturated, it means that there are all single bonds and every single bonding pair is filled with hydrogen atoms. So it tells us the number of hydrogen molecules a molecule needs to become a saturated non-cyclic compound. So if you have hydrocarbon CXHY, you would find the IHD in the following way. So it would be 2x plus 2 minus y divided by 2. And that will tell you your index of hydrogen deficiency. So in our first example, we're being asked to find the IHD for benzene. So that would be, so remember, IHD is equal to 2 times the number of carbon plus 2 minus the hydrogens over 2. So we have 6 carbons, so 2 times 6 plus 2 minus 6 all over 2. So that adds up to 8 over 2. So the index of hydrogen deficiency for benzene is 4. So we don't always work with hydrocarbons, however, so we need to follow a few other additional rules. So oxygen and sulfur don't affect the IHD. So you only add up the carbons and hydrogens in molecules that have those. So if you had ethanol, C2H5OH, we would say that there are 2 carbons and 6 hydrogens. You count halogens as if they were a hydrogen. So CH3Cl, we would say we have 1 carbon and 4 hydrogens. And then anytime there's a nitrogen atom, you substitute in one, or count 1 carbon and 1 hydrogen. So C3H5N we would say has 4 carbons and 6 hydrogens. So we'll apply some of those rules to calculate the IHD for each of these ones. So for the first one, it's just a regular hydrocarbon. So there are 7 carbons and 5, 6, 7, 8 hydrogens. So now what we'll do is we'll calculate the index. So we have 2 times carbon, so 2 times 7 plus 2 minus 8 over 2. So that would give this one a hydrogen deficiency of 4. So for the next one, it has an oxygen, but remember we don't count the oxygens, we just count the carbons and the hydrogens. So we have 2 carbons and 6 hydrogens. So our IHD is equal to 2 times 2 plus 2 minus 6 over 2. So that is equal to 0. The next one has a halogen, so we count that as a hydrogen. So we're going to say we have 3 carbons, 8 hydrogens. So our IHD is equal to 2 times 3 plus 2 minus 8 over 2. So that's equal to 0 as well. All right, so our next one gets a little more complicated. We don't worry about the oxygen, but this needs to add on another C and another H. So we have 2 carbons and 1, 2, 3, 4 hydrogens. So we'll calculate our IHD. So that's going to be 2 times 2 plus 2 minus 4 all over 2. So that's 4, 5, 6 minus, so this is a IHD of 1. So infrared spectroscopy is used to identify the bonds that are found in a molecule. So infrared radiation is absorbed by some bonds, and that causes them to stretch and bend. And we can use this information to determine what kinds of bonds are in the molecule. If a molecule has asymmetrical stretching, like this one here, so the carbon is stretching towards the oxygen and the other one's stretching away, or we have bending, then the dipole moment on the molecule is altered and it is said to be infrared active. So polar bonds are active and non-polar bonds are not. So this is an example of an infrared spectrum. There are two regions in a spectrum. The first part, the part that runs from 450 to 1500 centimeters -1, is called the fingerprint section. So that's unique to every molecule, but it's very messy and it's kind of hard to interpret because it's all jumbled together. So if we had a known spectrum and we compared it with an unknown spectrum, we could actually line it up just like with a fingerprint and realize, okay, this is the same thing, so it's this compound. However, we can also take a look at the functional group region. So that's everything beyond the 1500. And that's used to determine the types of bonds and functional groups. So we can find the data booklet, section 26, has all the full list of the data for all the different functional groups. So it'll tell you the type of bonds, what type of organic molecule it's found in, the wavelength number, and the intensity, whether it'll be a strong or a weak banding pattern. So the ones that are below 1500 fall in the fingerprint region. So these ones will be hard to interpret. So we won't be able to examine or make conclusive decisions about these ones. But we can make conclusions about alkenes, aldehydes, and ketones, so a carbonyl or a double bonded carbon, or a triple bonded carbon, or a hydroxyl, and so on. Those are all, we're able to interpret those ones. So this is the infrared spectrum for ethanol, and there's a few things that we can see here. So there's a peak around 3200 to 3400, so right here. This indicates the hydroxyl group, the OH. There's also a peak here around 3000. That indicates that there are carbon-hydrogen bonds, so single bonded carbons to hydrogens. There is a peak here around 1050, and that would indicate that it's a C double bonded O, or C single bonded O, sorry, but it's in the fingerprint region, so we can't be certain it's actually due to that bond, so we can't identify that one, but we know there's a hydroxyl, and we know there's single bonded carbons to hydrogens. So this is another example. This is methoxymethane. So this is an ether. So again, we can't be certain about this one right here, the C to the O, single bonded O, because it's in the fingerprint region, but there still is that peak around 3000, and that identifies the carbon-hydrogen bonds, but there is not a peak at 3200 to 3400 like there was in ethanol, so there's no hydroxyl found in this one. So this one, we see a very strong absorption around 3000, and that indicates that there's a carbon-hydrogen bond. So this is for methane. This type of pattern would be common in all hydrocarbons. So this one, we can see that there's a peak again at 3000 for the carbons and hydrogens. You'll always see a peak here. And then we also see another peak around 1700 right here. And that corresponds to the carbonyl that's found in propanone. So the C double bonded O is right there. So we can also use mass spectrometry to figure out what we're working with. So remember when we learned about figuring out percent composition by mass, we can use a mass spectrometer to determine the molar mass of an element. It can also be used to identify the identity of an organic compound. So in the mass spectrometer, the sample will be bombarded with high energy electrons. This will ionize the molecule. So you'll end up with this molecular ion. And then that molecular ion will be further fragmented to form a cation fragment and a radical fragment, and so on. So we can then look and identify. So this radical cation, we can figure out the molar mass of that, and that would be the molar mass of the compound. And then we'll see peaks where these other cations are formed. And they'll have specific masses, and we can then make some inferences. So here's an example. We see a few things here. There is the furthest to the right peak, the largest peak will be the molecular ion peak. And it's at a mass charge ratio of 58. This means that the molar mass of this compound is 58 grams per mole. And then we can also see that there are fragment peaks at number 43 and at 15 as well. So we already know the identity of this molecule. So it was actually propanone. So right here, so when it fragmented into a methyl, and then this part with the carbonyl still attached. So when those two things fragmented, we were able to figure out, based on their masses that they made in the peaks, what identities they were. So our data booklet in section 28 gives us a list of commonly observed fragments in mass spectrometry. So if there's a mass of the fragment of 15, then it's a methyl group. If it has a mass of 17, it's a hydroxyl cation. If it's 18, that's an H2O. 28 would be a C double bonded O, or an ethene. 29 would be this or this. 31 would be CH3O plus. 45 will be the carboxyl group. So we can now make some inferences on some mass spectra that we see. So this is an example from our Cognity textbook. So we've been presented with a mass spectrum. So we're being asked to determine the molar mass of the molecular ion, the fragments that correspond to the peaks at the mass charge ratio of 15 and mass charge ratio of 45. There was a typo on their thing that should say 45, not 43. And then the name of the compound. So the first thing is the largest peak will be the molar mass of the molecular ion, so it's 60 grams per mole. The fragments that correspond to the mass charge ratio of 15 and 45. So we look up in our data booklet under section 28, CH3 was the first one, and then the other one was carboxyl. So we have CH3 and a COOH. So the name of the compound is ethanoic acid. It's a carboxylic acid. Our final type of spectroscopy that we're going to examine is NMR spectroscopy. So it uses radio waves to detect the presence of protons in a molecule. And it's used to detect atoms that have an odd number of protons. If you use 31P NMR spectroscopy, you can use that in medicine to detect the damage to the heart, and then also explore the effects of diabetes on the body. H1 NMR spectroscopy is used in body scans or MRIs. And we use the spectroscopy to detect the protons in the various molecules. So whether it's in lipids, water, and so on, and they give us different signals. So a full body image can be produced. So when we look at hydrogen NMR spectroscopy, atoms with an odd number of protons can spin clockwise or anti-clockwise. So that creates a magnetic field. And when they're placed near an external magnetic field, some of them will line up with the field and some of them will line up against the field. So we end up with something that looks like this. So the peaks identify the number of environments the protons are found in. So this is a spectrum for ethanol, and there's 3 peaks. The peaks are called the chemical shift and are measured in parts per million. And these shifts are measured relative to a molecule called TMS, which has a relative shift of 0. So section 27 of our data booklet has the common shifts. So for the molecule in the example that we just looked at, there was a shift at 1 parts per million, 3.5 parts per million, and 5 parts per million. So if we look at this example, we're looking at 2-methyl-1-propene. There are 2 chemical shifts. There's one for the 2 methyls because they're in the same environment. So there's the central carbon here, and then off of that carbon there are 2 methyls. So both of them are in the same environment in the sense that they're bonded to the same type of atom. And then there's a peak also for the this one, this CH2 that's bonded to the double bond. So in our second example, we have actually 3 peaks, even though there's 2 CH3s. These 2 CH3s are in different environments. This one's bonded to a carbon that's bonded to an oxygen, and this one is bonded to a carbon that's bonded to a CH2, and then there's the CH2. So there's one for the CH3 that's attached to the carbonyl, one for the CH3 that's attached to the CH2, and then one for the CH2 itself. So you'll see 3 peaks. And there's always one little peak right there at 0, and that represents the TMS.